All right, guys, here we go. Let's talk about just reviewing real quick yesterday. Wrapping that up here at the very end. Slideshow. So there are the Newton's three laws. Okay, we are past this point really going to spend a bulk of our time trying to better understand Newton's three laws and what they mean and how they get used and how there's kind of misconceptions along them. Okay, so you take first and second, for example. If a person's traveling along in their car, first and second, they just basically trade back and forth. What lets you know whether or not the car is in first or second?
If it's in first, there's no acceleration.
Right, and if it's in second, accelerating. Right. First law says you're constant velocity. You're staying constant velocity. Second law says there's an acceleration, so that velocity is potentially changing. And then we talked, of course, about the forces. So mostly you're going to deal with first and second law. You get to third law only when stuff starts colliding together or interacting with each other. Now, a lot of people make mistakes on third law. I'm going to remind you of a mistake that people make a lot so that when you're talking about that and thinking about that tonight, hopefully you don't. What if I said, what's the force diagram on me right now standing here? Gravity down, normal up. Okay, keep that in mind. Now I'm going to ask myself a question, and I'm going to warn you that a lot of people get it wrong. And that is, what is the third order pair? What is the equal and opposite force to force of gravity? That's one answer. Anybody else? What's that? So that's what most people try to say, and that's the one I wanted to pull out of you because that's what people want to jump towards. And maybe that's why you didn't answer, because that's what you thought. People want to go, oh, it's force normal. It's definitely force normal. And I wanted to address that. You are correct, right? That is what it is. Okay. For starters, whenever I ask for a third order pair, here's what you need to train yourself to do. One, when Spainhour said force of gravity, the first thing I need to think about is what two objects are involved in that force. If I say your weight, your force of gravity, what two objects are involved in that force? You and the Earth. So when I say your force of gravity, that's the pull of the Earth on you. So to get the third order pair, if you've done that, it's real darn simple. You just switch the objects. That's it, right? If there's a force of the Earth on you, then third order pair says there's a force of you on the Earth. Notice that that is on the Earth. In other words, we talked about this yesterday. If you weigh 150 pounds, that means the Earth is pulling you down at 150 pounds, and that means you are pulling Earth at 150 pounds upwards. Now, your 150 pounds will cause you to accelerate at 9.8 because you have about 70 kilograms of mass. Does that 150 pounds have the same effect on Earth? No, because it has 5.98 times 10 to the 24th kilograms of mass. And so we could take that number, take 700 newtons, divided by 5.98 times 10 to the 24th. But your calculator is going to spit out a very small number, or basically a zero. So let's talk about why people think force normal. Okay, well, people think force normal because you draw a picture and you go, oh, force gravity down, force normal up, those are equal and opposite. And they are equal and opposite, but third law is not the reason why. Why are they equal and opposite? What law tells you they will be equal and opposite as I stand here? First law tells you the reason they are equal and opposite in this particular case. A few other pieces of information that will hopefully help in the future. Number one, reasons why force normal is definitely not the third order pair. That's a law. How often do laws happen? Always. Is force normal always equal to force gravity? No. Is it always opposite? Is it always going the opposite direction? No. If I run into the wall, it's that way. If I run into the ceiling, it goes the exact same way. The final thing is force normal is actually what force? Actually what fundamental force? Nope. What's that? Electromagnetism. It's the electrons and electrons pushing each other. You cannot mix and match third order pairs between gravity, one fundamental force, and electromagnetism, an entirely different fundamental force. The idea behind third law is, if these electrons are pushing on these electrons, if the electrons in my left hand are pushing on the electrons on my right, then the electrons in my right are pulling on the electrons and are pushing on the electrons on my left. They have to happen at the same time. One pushes one while the other pushes back. Gravity works the exact same way, If this chair is pulling me that way, then I am pulling that chair the other way at the exact same time. Questions, concerns about that third order conversation real quick there? Okay, let's practice a little bit. Oh, actually, one more thing before I get too much further into this. So, to kind of lay out a little bit of kind of the overarching kind of path that we go on in here in physics. First semester is spent doing three major things. There are three major ways to describe motion, okay, to describe all the world around us. You've knocked out one of them already. Kinematics, 2D kinematics, vectors, all that. That is one whole entire branch of how to describe the world around you. The second one is basically right here on this page, Newton's laws. So that's why we spend the next week and a half or so getting better at this, understanding it. Today we start the transition of taking these conceptual ideas and bringing them over to a mathematical side that we understand a little bit better. And then there's going to be energy as well, which we'll cover in next chapter before the end of the semester, but that is ultimately the goal. The idea behind this is if you're looking at these three and I'm saying stuff and you get confused, please understand there's meant to be time so you can get a little bit more used to these ideas. All right, let's get rid of that. And let's head on to today's bell ringer. Today's bell ringer is this right here. Go ahead. Oops, not that one. There we go. Okay. So what I want you to do is I want you to draw 5 force diagrams. We have a person, this is the same person in all these examples. A person standing in a helicopter waiting to jump out. The moment right after they jump out of the helicopter. After a while of falling out of the helicopter. Right after they open the parachute, the moment after they open the parachute. And E is a little bit separate from A and D, because hopefully it doesn't happen, but what would it look like if they hit the ground without a parachute? After you've drawn the force diagrams for A through E, I want you to come along number 2 here, is just say label each of those with first and second law. Let's go ahead and do that now. I'll play a song, and at the end of that song, we'll go over this. Alright, seeing a lot of people done, we're going to go ahead here and see what you got. Okay. A few things I wanted to address within this. This is, of course, most of the things I do right now, especially forces are very intricate and how they work kind of get combined together. A lot of what I'm going to do is, yes, it's a practice to help you, but also kind of showing you something else at the exact same time. So let's start with the person sitting in the helicopter. What's your force diagram for them?
Force gravity down.
Uh-huh.
Force of helicopter on person.
I'd be fine with that. I would also be completely fine with force normal in this case. Okay. I know that I said solid immovable object. Obviously, a helicopter is movable, but relative to us, I'm going to say it's relatively solid and it's not moving. There's some tricky stuff there on when you can, when you can't, when you shouldn't. We'll talk more about that moving on, but just know that you could use force normal here completely fine, and that would be okay. All right, second one, person right after they jumped out of the helicopter. What do you got? Yeah, I would just have force of gravity. I mean, if you put friction at all, you shouldn't have very much. Okay, but I would honestly say none. And the main thing that you're looking at the wording up here to let you know that is right when they jump out of the helicopter. Now, you might get really pedantic here and kind of like into the weeds and be like, well, technically, one year somebody goes like, well, technically, isn't the blades of the helicopter pushing air down? Yes, that actually would, and so friction would actually be down in that case. We're not worrying about that for right now. All right, what changes though? Now we've got a person after a while of falling. Why should C be any different than B?
It's a while, so there's friction.
Yeah, and actually, let's think about this carefully. Kind of, if I could watch this person's force diagram in real time, okay? If I was watching it in real time, what would change?
The air would go up.
There we can figure. Until when? No. Well, okay, I see where you're going there. Yes, I'm fine with that sentence, but probably a better way to put it. Yeah, until it's equal to force gravity. Why? There's what I was looking for, as a matter of fact. Yeah, at equal forces between the two of them, this situation right now is known as terminal velocity. Terminal velocity is reached when the friction pushing up is equal to force gravity pushing down, and so what should happen to their velocity at that time? Stay constant. Now that constant is a little bit tricky because of a couple things. Let's say this. Let's say you got your person in that situation and they decide to do that action star thing, right? They lean forward, okay? What does that change? What changes about the force diagram if that person does that pencil action star thing? Like this is
not a friction.
Why?
Because the air changes.
You're right and wrong. We want to hit basics here because a lot of people want to say this, and if you're saying this, it's fine, but we need to move away from it. Anytime you have to explain something like it's more aerodynamic. I mean, like I'm just trying to make sure that everybody knows, okay? Because I'm not saying just you, but like a lot of people go, well, no. If you can't use basic words to explain why something is happening, then you don't understand it yet. So what is the basic reason why this is my person? The pencil will cause less friction.
More electrons.
Why?
Like space.
So?
Like,
Sorry, Jaden, I was kind of going way through there. What'd you say?
more electrons are repelling. Or less electrons.
Less electrons, yeah, and probably the best way to say that, you're right there with it, the less surface area. You have less surface area to hit electrons, you're hitting less electrons, so what about that force diagram would change? The third one there. Friction would get a lot less, and if friction gets a lot less, what happens to the person? They go faster, until when? No, you're fine, you're right, they'll go faster until when?
The forces are equal.
The forces, once again, you go faster and faster, you get more and more and more and more electrons. If you get more electrons, eventually, once again, that friction is going to grow until it's equal to force gravity. Now, let's say you're going faster. You're going faster, okay, that faster speed, and you decide to flatten back out again. Now you're going faster, and you have a lot more surface area. How does the force diagram change?
Friction gets really hot.
Which brings us to the fourth one up here. What's the only thing a parachute does? Expands you so you can hit more electrons, and therefore you have more force friction. So the answer to this one should be force of gravity, and then force friction should be a lot bigger. Now, what people get confused on this is they go, wait, Spainhour, if you draw that, the person's not going up. No, they're not. What is pointed up in this force diagram because of this? Acceleration. And as we know, which way is the velocity going? Down. And if the velocity is down and acceleration is up, what will they do? Until when?
They reach or they
No.
Forces are balanced.
Until the forces, yeah, that friction's going to get smaller and smaller and smaller until you get slower, slower, slower. So really what a parachute does is it decreases your velocity down until your legs aren't going to break when they hit the ground because your legs don't have to provide that acceleration. Okay, I'll get to that question here in just a second, I promise. Cool thing about this real fast that I found out recently, squirrels are one of the only animals that can naturally get terminal velocity just naturally on their own, and they survive just because of that. The first thing that benefits them is the fact that this force gravity is a lot less. So they're affected a lot more by friction because their force gravity is smaller. But also, they can spread themselves out in crazy areas. So it's actually scientifically proven, weirdly scientifically proven fact that you can throw a squirrel from literally any height on Earth, and it will survive. As long as it's not a dumb squirrel. But yes, Trent.
What if you did force tension?
I'm going to talk about that here in just a second. That's an excellent question. But I would probably suggest not, but we'll do that here in just a minute. Let's finish E, and then we'll move on. Actually, we're going to finish E, part 2, and then I'm going to make sure and address that as well. All right, E should just be this. Force gravity down, and I don't have enough space, but force normal is up, much bigger. That's, of course, why you... So it's not the fall that kills you, it's the sudden stop at the end. Yeah. Internal bleeding. So, yeah, that's definitely going to do it. Let's knock out 2 real quick. Let's hit all of these with the first or second law. First one is? First, what are the 2 reasons why it's in first? You can say either one.
unchanging velocity.
No, or constant velocity is probably an easier way to say that, but yes, that's one way to say it. And what's the other way you could tell me that that's in first?
Balance forces.
Forces are balanced, correct. All right, and then of course, right after you jumped out, this person's in second. Very good. Unbalanced forces, as well as they're accelerating. Terminal velocity is first. Balanced forces, constant velocity, and then both of these 2 over here are second. Very good. All right, the question that was brought up, and it is an excellent question. On the parachute one, could I say tension is up? And arguably yes, although I wouldn't highly suggest it. How do I know the difference between the 2, friction or tension? It goes back to that conversation we had with the person on the swing when we did force diagrams the other day, and where you define your system, how you define the thing. Like, do you technically consider clothes as part of you, or are they separate? And the answer is yes, you could do either one. It's completely fine. And you remember what I said was, when you define your system, it's kind of like you draw a circle around the system. So if you did it kind of like this, you thought about the force diagram on the person, then yeah, you would say it's tension that's actually pulling on those. But that's a little bit confusing because why is tension happening? Tension's happening because of friction's happening, so you got friction causing tension causing. So me personally, when I do this, I define the circle like this. It's the person parachute system, in which case it's friction that ultimately affects them in that particular case. Am I going to mark one off versus the other? No, but as I just mentioned, the tension one can cause a little bit more issues when we transfer to mathematics here in just a minute. And this is probably the easier one to kind of understand fundamentally in that particular case. Main thing is, don't do both. Don't do both. That will mess you up severely. Questions, concerns here? Okay, let's move on to today. So today, what we're trying to do is we're going to start trying to transition, as I mentioned, this like conceptual ideas over to like, okay, but how do we tackle this a little bit more mathematically at the same time? Okay, and the assignment with today is called Forces as Vectors. The reason it's called that is because it's drawing on your understanding of vectors. For example, 1 and 2 up here are super simple, okay? They are just basically trig. Hey, 70 newtons is directed at 30 degrees to the horizontal, find the x and the y. And the second one, a man pulls with a force of 25 newtons at an angle 72 right of the vertical. The main reason I'm highlighting them right now is this is just trig. You're good on trig. But is because we are getting rid of a simplification that I told you that we were making last chapter. And I reminded you of it because we were getting used to it, but we are now getting rid of that simplification. So let's make sure and talk about that briefly. What do I mean? Well, the first example said, I think it was blah, 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 70 newtons at 30 degrees to the horizontal. And it asked you to find the x component and the y component of force. Now, I'm not going to fully do this for you right now, but I want to point out in this particular case that, of course, the x is the adjacent. And therefore, cosine goes with x, like you were used to. But if you look at problem number 2, on problem number 2, it says that the angle is 72 degrees right of the vertical. So that is your angle. And if that's your angle, you have to learn to draw your triangle like this. You draw the first line of the triangle, but the adjacent side is the one right next to the angle. Okay? In this particular case, notice that the x is the x the adjacent anymore. No. Sine is going to get you the x, and cosine is going to get you the y. The inevitable thing that any student will ask me is they go, Spainhour, can't I just do geometry and tell you that the other angle is 18? You can. There's certain times in here where I will push like, hey, do whatever the heck you want. It really doesn't matter either way. And then there's times where I'm going to be like, yeah, you should learn to do it the other way because it's going to be easier for you in the long run. That's one of these cases. You really don't want to, like, every single problem be reliant on getting that angle at the right spot. You really want to be reliant on just knowing good trig. And trig, it's very clear, does not go anywhere with x or y. Does not. Okay? So how do you figure it out? Take 5-10 seconds, draw the picture. Draw the picture. And it's not going to take you long. I will tell you that I still yell this exact same thing to my Physics 2 students. Like, we don't understand what trig to use. Have you drawn the picture? No. Go draw the picture. It will take you less than 5 seconds, and that will answer your question for you on which trig you're supposed to use. I don't know why students feel like they have to have this like just internal, like just know, and they get mad at themselves if they can't just draw the picture, and it answers the question for you. Okay? So make sure that you're addressing when it says, the key thing is most students look at 30 degrees and they ignore everything after it. Or they see 72 degrees and they ignore everything after it. Nope. This says 30 degrees to the horizontal. To the horizontal tells you where to start, tells you it's with the x, tells you it's that first triangle. This one says right of the vertical, tells you where to start, draw that 72 degrees. Questions, concerns about those comments? Let's move on. We're going to skip ahead. We're going to do number 8 here. Okay? So if you want to get out homework or whatever, so you have this one done, that's completely fine. This says find the resultant force for the figures over on the right. Now when it says find the resultant force, okay, I mentioned the other day this is the same thing as sum of forces, force net, sigma f, all of these are the same thing. But ultimately, here's all that means. Hey, are forces vectors? So how do you get the resultant of vectors? What's it called? How do you get the sum of vectors? I'm basically saying it without saying it. Vector addition, yes. You have to do vector addition. So there's 2 ways to look at this. We're going to do it in the old way that you understand previously. First, let's go ahead and open this up, and then we'll do the other one. Where did it go? Where did it go? Where did it go? Oh, darn it. Did I erase that? I don't think I did. There it is. Okay, cool. All right, so we're just going to do the vector addition. So you'll notice that these arrows are drawn not in your standard vector addition way. They are drawn in a force diagram way, tail to tail, okay, or from the center. We need to draw them, of course, tail to tip. That's how we always do vector addition. So if I'm just sketching this, it's going to go 400 to the right, 300 up, and then 200 is, down and to the left here, and my final answer will be this guy right here. So you'll notice you don't see any angles, but you do know all of them. What is the angle for the 400? 0. 400 Newton says 0 degrees. What's the angle for the 300? 90 degrees. And what is the angle for the 200? Nope. 210. So I'm gonna have you guys take about 5 minutes and do this vector addition here real quick, just in the standard way, giving you those angles right there. Now, before you get too farther, I'm gonna tell you that there is a simplification that I would highly suggest you start to get used to, and that's this. Usually in vector addition, it comes in 3 steps. 3 steps are break these all down to their x and y's. Second step, add all the x and the y's. Third step, combine x and y's back together. What I'm going to suggest you do is combine the first 2 steps together. Instead of just finding all these individually, calculated them all out individually, and then adding them, just do that as one big step so you don't have to do a bunch of extra writing. Meaning, if I want to find x total, for example, how would I find the x of the first one? What's the trick? I mean, I know you 100% can just like you know what it is, but 400 cosine 0. So this is how you would find the x value of the first one. Then you add that to the second one. Then you add that to the third one. And that will get me my total. A little bit more efficient, get you done a little bit faster. All right, so go ahead and do that vector addition. I'll give you about 5 minutes, and then we'll continue on. Just so you have kind of like a better picture of kind of what this is like conceptually. Like, what am I doing? What am I solving for? This would be like, imagine, if you will, that there's somebody right here in the middle of 3 people, right? And all 3 people want them to go a different direction. So they're all pushing in a different direction. They're pushing real good, okay? So they're trying to push it real good in a different direction. Three different people.
Why is it all cosine instead of the main sine?
Do what? What did you say?
How are they all the x? Like, they're like 300 is opposite of the angle.
300n is opposite of the angle. What did you say? I'm confused by that.
Wouldn't it be? I'm confused why it's not sine because it's opposite of the angle.
Well, I'm finding the x of that. If you were finding the y, then you would use
On there.
Now, ultimately, I've done something here that you probably wouldn't do because you would simplify it in an easier way. Yeah, you certainly can. If you type it in like that, that's going to get you your x total. It's going to be a lot more efficient. Here, I'll tell you what the answers should be of x total and y total real quick. X total better be 226.8. I think y total should be 200. You guys notice this, but salt and peppers here. Salt and peppers here.
And that's new, right? The value.
Uh-huh.
I didn't know if you were supposed to do that. Wait, is this right?
Yeah, what's up, Keith?
So, the conversation that you had earlier about us moving away from the understanding that the angle is always going to be measured from the x. Whenever you do, like the tangent function, is it still y over
Not
x?
tangent.
Or inverse tangent?
Yes, I see what you're saying. I see.
Is it
Yes.
still y over
Inverse
x?
tangent is telling the calculator which angle you want. So, yes, it still is. I mean, the standard way of measuring an angle is from the x. So that's why we want to have opposite y and adjacent x. No, you don't change that at all.
So
As a matter of fact, you'll notice in this particular problem, none of the trig does change because all the main angles are measured with the x. All right, I'm going to get going here. Your final answer should have been here. Let's just show you real quick. It should look like this, as I already sketched. There, there, there. And the final answer, if you've done it correctly, is 302.4 at 41.4 degrees. Yes? Or your total x should be 226.8, and your total y should be 200 y halves. Is that about right? Okay. All right, so I'm going to continue on here, even if you didn't finish that, because I wanted to address, I said, there's two ways that we can do this. What I want to show you right now is the second way of doing this that is arguably a little bit faster and easier and important for what we want to do. As these are forces, here's what I technically just did. I just found the sum of forces in the x. Okay? So how we're going to do this a little bit differently, although it's not different at all, is what I want you to do is I want you to look at, I know you guys are finishing the vector addition. Stop. You want to see this. You do not want to miss this. Okay? You can finish the vector addition later. You'll get the right answer. We'll all be proud of you. Okay, and what I'm going to do first is I'm going to label these over here. Usually these are labeled already. I'm going to say that's A, that's B, and that's C. As a matter of fact, let's change colors so it's a little bit easier to see on there. Let's go A, B, C. Okay, and what you do is you look at a vector, every vector, when you're looking at the x, and you ask the following questions. Number one, is A on the x-axis? Yes, so I'm going to write it down. Number two, which direction is it on the x-axis? Positive. Final question you ask, is it only on the x-axis or is it split between the two? Okay, so what I do is I write A because it's on there, positive because it's in the positive direction, and since there's nothing else, I just leave it alone. That all of A is on the x-axis, that's what that says. Next, I got a B. Is B on the x-axis? No, skip it. C, is C on the x-axis? Yes, positive or negative? Negative. Is it only on the x-axis? No. So I'm going to put negative C, and since it's on both, I need to distinguish. Meaning, when I write minus C to the x there, what I'm worried about is how much of this vector right here, that is Cx. How much is on the x-axis? See if you can't do that exact same thing now for the sum of forces in the y. Do that really quick. As always, 7th hour physics after school. On Tuesdays. Just a quick heads up. Science is doing a thing now for tutoring across all of science. There is the possibility now today that I will have other people from other classes coming in as well. So there'll be a sign-in sheet. It's not a big deal. Again, you're always welcome in. All right. What do we got? What should this look like? Plus B minus CY. Now, why is this helpful? Well, why it's helpful is that I just did what we did earlier, but a lot faster. What is this? This is 400 newtons minus 200 newtons cosine of 30. Now, you might say, Spadenhauer, why did you use cosine here and earlier, why did you use cosine of 30 there and earlier used cosine of 210? Do you know what the difference is between the cosine of 30 and the cosine of 210? There's only one very small difference, okay? Cosine of 210 is a 30-degree triangle. It's a 30, 30, 60. It's just done down in the third quadrant. So the only thing that is different, and feel free to punch in your calculator right now, punch in the cosine of 30 and then punch in the cosine of 210. Have 2 or 3 people do it. Tell me what the difference is. The sign. It's it. So, correct. If I've already addressed the sign right here, do I need to address it again? So I'll tell you, me personally, moving past this spot, you will never see me use an angle that is above 90 degrees again. I'm using all of my angles, and I'm just going to go ahead and personally take care of the sign in what direction they are going. Now you do all that, what answer do you get? The exact same answer you got just a second ago. And same thing here. That's 300 newtons minus 200 newtons sine of 30 degrees. And that gets you 200. There we go. Y hat. Same sort of conversation. This method right here of summing the forces in the x and summing the forces in the y is going to become very, very helpful as we transition in just a second to real-world examples. Now, this is problem number 8. I think problem number 9 on the homework looks like, where'd it go? This one. So what I want you to do just real quick is do the sum of forces and the x and the y for this. Like just write that equation. That's all.
Problem is this?
Number 9. It's the very next one.
Okay.
Is it exactly the same number?
I believe so. I mean, I copy and pasted off of number 9. So if it's not, I don't know what's up. So that we're all getting the same answers, let's go ahead and call that A, B, and C. It doesn't matter. The letters don't matter. The only reason I'm doing it right now is so that we can all agree right now that we're getting the same thing. All right, let's not take too long here. What's the sum of forces in the x? Start right up here. Start with A. Positive AX. Okay. B minus B. And plus CX. Very good. Why is it plus and not negative?
Because it's lines in lots of x directions.
Yeah, and one thing that people will struggle with here is, the reason I ask that question is I go, but it's down. Don't forget, you're mixing up x and y. When we're talking x, we're only mixing with x, right and left. So, sum of the forces in the y. AY what?
AY plus.
No, minus CY. And notice, by the way, that my AXs are both positive because they're in the first quadrant. And my C is positive in the X and negative in the Y because it's in the fourth quadrant. Very good. And B is none of those because it's not in a quadrant at all. Now, a couple things here when you do this. If you use my particular method, which I'm completely fine with, when you go to find the cosine of A, when you go to find the x value of A, what trig function should you use? This is AX right here. What trig function should you use? Use cosine, of course, your standard way. But when you go to use this one, whenever you draw an angle, the way you draw that picture is you draw the adjacent with the angle first. So if you want to find the x for C, what are you using? Sine. Is everybody following that? Cool beans, we're moving on. Okay, so the whole goal of this, we start off very arbitrary here, taking vector addition into kind of this more stylized way of doing it, but it's all just vector addition. As a matter of fact, if I come back here and point this out, so our equation that we got was A minus CX and B minus CX. Well, if you look at this equation, watch me simplify this to an extreme amount. Cosine of 90 degrees is just 0, right? There was really no reason to put it. If you didn't put it at all, that's fine. And cosine of 1 is just 1. So what's 400? That's A. And that over there is minus CX. So they're the exact same way, they're the exact same things, just this way is a little bit faster, a little bit more efficient. It kind of covers everything it is that we're trying to do all wrapped into one at the same time. Okay, so it's all just vector addition. Like you see here, we get the exact same answers as we did before. Now what we're going to do is we're going to try to combine all this stuff. Okay, we're going to try to combine force diagrams, all the forces and stuff into kind of a process where we can talk about this math in general. I need a volunteer to come up and be pulled in a chair. Just a heads up, I do need to measure your mass ahead of time. It's going to be mass and not weight, if that bothers you. So I need a volunteer to be pulled in a chair. All right, come on up. I'm gonna have you stand on the scale first to get your mass. It's right over there. Wherever. I'm just gonna say it on the other side, but your call. All right, so let's go 67.7. We'll just round up to 68 kilograms. So, okay, and now I need you to sit in the chair. There you go. Look at you ahead of time. Okay. This scale on here, okay, is going to measure how much oomph I have to push with in order to pull her. So what we're going to do is I'm going to pull her across the room, starting to rest. As a matter of fact, if you wouldn't mind, Kenzie, scooting back a little way so I have a little bit more room to do this. And Kenzie, what I'm going to need you to do is I'm going to pull this. And this number's going to bounce around a little bit because of bumps and stuff in the ground, but I need you to try to see roughly where it sits when we're about at constant velocity. Okay? Not an easy thing to do, by the way. But now this thing right down here, this thing will measure the maximum, so I'll talk about that because we'll need that one as well. But again, right now you should have the mass is 68 kilograms. So go ahead and hold on to that. Good, it's just right there, okay? And I'm going to pull you hopefully at a constant velocity. We'll get you going here, get you going, okay now. What do you got? Good.
4.4 1/4. I can't think of the 4.2.
You want to be on pounds. Let's go back to the opposite.
My bad.
It's all right. I should have warned you ahead of time. Okay, so this is kilograms. We don't need to worry about kilograms. We need that over there. So let's go back. Get you going. Okay, very good. Thank you very much. So, things that we need to know now. It took 9 pounds of force, okay, to keep her going at a constant velocity. But also, we're going to need this number for tomorrow when we come back to it. It took about 18 pounds of force to get going at the very beginning. So, what I want you to do right now, first, draw the force diagram of Kenzie when she was being pulled at constant velocity throughout the room. And then a little ways down on your page, kind of like scoot down a little bit, draw a second force diagram of what was different when I first got her going. The first force diagram is her being pulled at a constant velocity across the front of the room. And the second force diagram is a little different, not much. What is different about that when she's pulled, when she's changed at the very beginning? We built that rabbit because I told my advisory students today that we were going to build a bunch of rabbits and we were going to bomb someone's desk. Like we were just going to pick somebody and put like a bunch of rabbits on there. It didn't work because I was the only one who didn't give up. This is one person's attempt at the rabbit. This person got closer. This is a very stylized rabbit, by the way. Like they kind of like abstract rabbit. Rabbit adjacent. To the ears. What's up? Just wait, she first gets up. All right, let's draw the force diagram on her. When she's being pulled at a constant velocity in the chair. What's force diagram? Agreed. Force of gravity. What else? Force normal. And I would probably say force normal in this particular case, although chair on person will work somewhat similarly. I'm going to say force normal up here, though. What else?
Force tension.
Force tension. Okay, you could say force tension would be one option. We could also say scale on person, either completely fine. I'll go with tension. I like that. And we know this is not the final process, because if this was the final process, she would not be at a constant velocity. Force friction. And what's true of all those forces? They're all balanced. So the information that we currently have is mass is 68 kilograms.
I have a question.
Mm-hmm.
So how do you know that like the force of gravity vector is longer than like the force tension or force?
Because I personally know. I will show you how to get the numbers here. That's why we're working on it right now. You shouldn't know yet. Because I've done it for 16 years is the answer to that question. But you haven't got there yet. How I technically, I'm not even drawing it anywhere close to what the actual size is. But if you're on a test and you drew all of these the same, I would not bat an eye. I wouldn't worry about it too much yet. Okay. All right. Kenzie, what did you say? What was the scale when you were going constant velocity? 9 pounds? Okay. Force tension is 9 pounds. And then that other force tension of 16 pounds, put that on your page so we remember that for tomorrow. I'm not putting it up here because it's not yet for this problem, it's for the next one. And what we're going to try to find is we're going to try to find force normal and force friction. Now this is a relatively simple problem of which you would not need the work I'm about to show you. You're going to want to know how to do the work that we need. I mean, standard stuff I say at the beginning of every single math of every single chapter is like, I'm going to start with an easy example. I'm going to start with an easy example so that you learn this methodology. So when things get more complicated, hopefully eventually we learn to trust me a little bit. But if you know, it's fine. All right. Now before we get too much into this, I'm going to kind of do a hop, skip, and a jump over to another example, which is very, very important. So let's imagine briefly that instead of pulling Kenzie on a chair, we Sparta kick her off of a building. So this is Alton. All right, anyway, so not important. What's the force diagram on her after we kick off the building?
Gravity.
Gravity. That's pretty much it, right? Now, try to follow this line of logic because this gets us to another possible equation that we're going to use. Right now, the only equation you really have under your belts in this chapter we learned yesterday is this. What is that equation called? Newton's second law. That is Newton's second law. Now, the reason we might ask why do we do Newton's second law and not Newton's first is that actually Newton's first is buried inside of Newton's second law. Because in Newton's first, what's true of acceleration?
It's 0.
It's 0. In which case, that would be 0. In which case, we get, yay, Newton's first law. But obviously, that's not the case for Kenzie. In this particular case, she is not accelerating at 0. But do we know how much Kenzie is accelerating after she's been kicked off the side of the building? How much? Negative. Not negative. Remember, negative is only because why? Why is it negative? Why? Yeah, so it's not. It's not inherently negative. It's only negative if you decide that it is. So what's important here is that she's accelerating at 9.8 meters per second squared down. Okay, down, and that will really come into play when we start doing this math. So it's very important. I'll say it more simply. G is not negative. G by itself is not negative. Now, in this example, the sum of forces is all of her forces added up, but there is only one, right? So that would be force of gravity. And how much is she going to accelerate? At G. So acceleration is G. These two equations look stupid close to each other. Like most students are like, they're basically the same thing. Oh no, they're not. Oh no, they're not. Get that down. I'm going to follow my line of logic here again in just a second because it's really important that you understand this. Yesterday I defined a Newton. A Newton is 1 kilogram accelerated at 1 meter per second squared. When I say I define something, what I'm saying is whatever force it takes, I don't know, whatever it takes to accelerate this 1 kilogram at 1 meter per second squared is 1 Newton. So if I have to accelerate this at 9.8 meters per second squared, guess how much force that takes? 9.8 newtons. And if I have to accelerate Kenzie, 68 kilograms at 9.8, this is how much force it takes. Hold on, let me finish here real quick and then I'll move on. This force of gravity, she's accelerating. Is she accelerating in this earlier example? No. But is that force of gravity the same as that force of gravity? Yes. So can I still use this equation to find her force of gravity over here? Yes. We'll finish that up and talk more about that tomorrow.